I'm going to go ahead and get started then. So we have been talking about the four forces of flight. We did weight last class and we began talking about lift. I will do a brief review about lift, since I didn't get too far last class. So lift is a force that acts perpendicularly and perpendicular to the flight path, so sort of up into the air. And it's caused by a difference of air pressure along the wing. And I'll go more into the theories of lift since we still don't entirely know why it works, but if anyone asks, the theories that we discussed will be very important. They are the definite theories for why planes fly. Anyway, sorry. Lift is sensitive to both the airspeed over the wing, so speed of your aircraft does make a difference on how much lift that it is generating, as well as the angle of attack of the wing. Does anybody know or remember what the angle of attack stands for that I discussed last class? Anybody remember what I went over? It sounds a lot cooler than it is. But it's still pretty cool, I think. The angle of attack is basically the angle between the wind and the wing. So basically, if you are lifting off, for example, the wind is going to be hitting your wing. The higher this angle of attack is, so the more horizontal or the more vertical it goes, in general, the more lift that will be experienced by this wing here. So we can actually use the idea of an angle of attack and sort of create a built-in angle of attack when we were to design our airplanes. So a built-in angle of attack to a wing is called an angle of incidence. So if we're looking from an airplane from the side, this would be the long part, the longitudinal axis. An angle of incidence would be tilting the wing up so that just by default, when your aircraft is on the ground, for example, it's getting extra lift just because of this tilt of your wing. So aerospace engineers will often add an angle of incidence to increase their lift, and to really increase your lift, for example, when you're trying to take off, they point their nose up and give their wing an angle of attack. Okay? So what we were working on last class... Sorry. Oh, where was I? What we were working on last class is taking a look at what we call the lift vectors along the wing of an airplane. So what we did, we made sure that we were using the Cessna 172 Skyhawk, just like usual, and we go and click on Special, and then click on Show Flight Model. So I already have it up, so I don't need to do that. But what we will see once we do that, inside the cockpit we can only see these white lines which are caused by the propeller. Okay? And when we're on the ground, when we're on the ground, I'm going to show you real quick, there is not any lift existing on the wings. There's not these nice lift vectors that you can sort of see here. And that's because we don't have any lift. If you all remember, lift varies based on the speed of the air going over the wing. So basically that would be making sure the plane would be moving, and also the angle of attack. Obviously it's stationary. While the plane might have a small angle of incidence, it's not moving, so there is no lift. Alright. except for the little bit of thrust caused by the propeller, but that doesn't really matter right now. We'll go over thrust next class when we talk about our final force of flight. So what I want you all to do, make sure that you have gone to special and then show flight model. But I do also want you to go into your quick flight setup, and we're going to we want to make sure that we're in the air. We're going to do a final approach. We're not necessarily going to land right now. I'm just doing this so you can see how the lift changes. We're going to do a final approach of 3 nautical miles. And Noah's saying that he's over the sea and he sees boats. And yep, they try to simulate what it would sort of look like. Obviously the graphics aren't too great, but yes, there are boats on the sea. So we're going to do a final approach on Loey, just like before. Hopefully everything else should be the same. You wouldn't have to change it. But once you have clicked on this 3 nautical miles, not nanometers like I keep saying, we can hit the X and then pause our simulation. Once we do this, we are going to want to hit A on our keyboard so that we can see our lift vectors. I would like for you to raise your hand once you're flying and you can see your lift vectors over your plane. And I can tell you to do it again if you need. We're going to be doing a little exercise with these lift vectors. Just want to make sure that you all are on the same page as us. Or me, rather, I guess. Does anybody want me to show them again what I just did to get these lift vectors and get the plane in the sky? Are we all good there? Just want to make sure that I'm not totally confusing anyone here. Got at least 3 folks that okay. So what I want you to do is fly level for 3 seconds. So remember, level is just trying to fly straight. And while you're flying, I want you to take a look at your lift vectors. They should look a little something like they do on my screen right now, actually. And so you'll notice that the lift closer to the fuselage of the plane, which is, the main body, is higher than the lift vectors are on the tips of the wing. So notice that the vectors here, these long lines, get shorter, meaning that there's less lift on the tips of your wings. Alright. You'll also notice a couple of tiny little other things. Oh my gosh, my keyboard's messing up. You'll see a couple of little yellow lines and a couple of little red lines. So I've told you that lift is the green lines, and I've told you that thrust, oh my goodness, my keyboard's messing up. The thrust is these white lines. Does anybody want to take a guess as to what these other lines could mean? If you remember the four forces of flight, what could these other lines mean? The yellow or the red? Any ideas? Throw them out. Don't be afraid. Drag. You got it. Drag is actually going to be the the red line. Notice that it's very small. This plane is optimized to minimize drag, which we'll discuss more in a little bit. All planes are. But the yellow line's a little bit weird, and I don't expect any of you to guess that because I had to look it up myself. The yellow line is horizontal lift. Well, that's kind of weird, isn't it? You wouldn't expect any horizontal lift to be occurring. But what I do want to let you know is that any part of the airplane that can be called a lifting surface produces lift in two directions. So obviously, lift is being produced upwards, which are these big green lines, but some lift is also being produced along the longitudinal axis of your airplane. Alright, so just a little bit of it is, so I wouldn't expect you to know that offhand, but lift is generated in two directions, not just one. Okay, so that's very weird to think about. Don't worry about it. You'll probably never need to know that in real life. So, once you've flown for about 3 seconds in level flight, what I want you to do is point it so your nose is going up a little bit. So, sort of like you would be ascending. And I want you to do that for 3 seconds and watch the lift vectors change on your aircraft. And I'll do it too, just so you can see, but I just want to show you what changes on your lift vectors here. What happens? Anyone want to mention what happens to the ones on your wing? It might be hard to see, so you might have to do another 3 seconds of keeping your nose up. Do these lift vectors get bigger, or do they get smaller when you point your nose up? I'll show you again. Bigger vectors or smaller vectors? They're actually going to be getting smaller as you point your nose up. And this is because you are losing speed and therefore are losing lift. Even though we have an angle of attack here, the lift caused by speed is a little bit more important in this case, just because we're not at full power like we would be if we were lifting off. You'll also notice, if my keyboard wants to work, okay, you can't see it here, but there's actually lift vectors that are appearing on your tail, called your horizontal stabilizer, and these vectors are actually pointing down. You can barely see one right here. This horizontal tail here does is a lifting surface, meaning it does produce lift, but it produces lift in the opposite direction of your wings. Or not of your wings, I guess of your nose. So if you want to point your nose up, your back tail here is producing lift downwards so that your nose can tilt up. So just a little cool aside there. Now what I want you to do is keep flying your plane until something happens to your lift vectors. And I'll show you on my screen too what happens. But I'm going to keep my nose up until I reach a certain point. And there we go. So you're saying you keep spawning in the ocean. I had a student that had that happen to him last class as well. Normally, or the way that they fixed it is by going into the quick flight setup, making sure Lowy was selected, and clicking go to this airport. If it still keeps happening, it's not too big a deal. As long as that runway on the ocean is visible, you'll be fine. You don't need to worry about it being Lowy. We just choose Lowy because it's a nice little airport. Pretty scenery, I guess. But once I keep my nose up for as long as I can before I start falling, these lift vectors get very small. Did y'all see that? You can sort of see it on my plane right now. How do you do what setup? You're saying click the land button, crash it, then click takeoff. I think it's something different than what you're saying to do, Lauren. Okay, so to go to quick flight setup, you go to settings, and then to quick flight setup. Then make sure Lowy is highlighted and click go to this airport. So you'll notice that when you keep pointing your nose towards the sky, that eventually your lift vectors will get a little bit smaller, and then something weird happens. And also, Noah, let me know if that worked, because I think Lauren has another option here. What happens at this point once your lift vectors get small and you start falling out of the sky? Anybody have any ideas? Small lift vectors meaning not a lot of lift. Anybody know what it's called when we lose lift rapidly? I've mentioned it a couple times now. Yeah, you got it. It's called a stall. Caused by a rapid loss of lift over the wings. And what happens is one wing will usually lose lift before the other, and so your plane will drop to one direction and start falling. So we actually stalled out here because, not because well, sort of because our angle of attack, but mostly because we've lost speed. How do we regain lift, though? If we've lost speed, it would make sense to want to regain speed so that we regain some lift, right? Now you're spawning in the water? Okay, weird. So the other option that I have for you then, you're saying click the land button, crash the plane, click takeoff to get off the ocean. What land button are you referring to, Lauren? And yes, you got it. You want to dive and then level out to regain lift and to not crash. So what you're saying, Lauren, is to go into your quick flight setup, land button, and then your takeoff button, and that worked for you? Go and do you have more to add to that thought? While you're finishing that up, what I'm going to do is have you go into your dive and check the lift vectors as you level your plane out. So, okay, so Noah, what I'm being told is to go to the ocean. In the About section, click on Land. Change the time of day in your quick flight setup. Crash. And then in the About menu, click Takeoff. That's what I'm being told. So you have a lagging flying aircraft. Luckily, hasn't happened in real life, but I think that is just an issue caused by webinar software mixed with this. And honestly, Noah, if Xing out of it and going back into it doesn't help, I don't know. I hope that would work. So again, what we're doing is we are watching the lift vectors as we recover from our dive and go into a straight level flight. When we dive, does our lift increase or decrease? Anyone? If lift increases with speed and diving increases speed, does lift increase with speed? Because the answer to that is yes. So to regain lift after a stall, we just point our nose down and level off. So Noah, has that worked out for you yet? Because I have more detailed instructions if so. No, you're fine. No worries. Collision reopening. Okay. I'm also going to send you exactly what I was told to do to fix that. Because I've had that happen a couple times, but it always would fix itself randomly, so I'm not really sure the exact answer there. Alright. So while you're working on finishing that up, I am going to go over the two theories of lift. The first of which is by this guy called Bernoulli. He's a very prominent name in the aerodynamics world. He had a lot of good insights on flying. But his theory of why lift happens ended up being called Bernoulli's principle. So we have a cross-section of a wing here called an airfoil, and we have a whole bunch of air molecules that are hitting it, hitting this very first part here. Some of the air molecules will choose to go on the top of the wing, and some will end up going on the bottom. The ones that go over top of the wing have to go a longer distance, but have to arrive at the end of the wing at the same time as the bottom, the air on the bottom of the wing. So the air on the bottom of the wing doesn't go very far. It's a pretty leisurely stroll here. So the air that goes over the wing has to go faster than the air on the bottom of the wing. This results in a pressure differential, so there's different pressure on the bottom and top. The bottom of the wing has higher pressure, and the top of the wing has a lower pressure. Pressure likes to go from high to low, so this high pressure will push up on the wing into this low pressure area. So another example of pressure going high to low, you shake up a soda bottle and open up the lid. That high pressure inside the soda bottle spurts out into the lower pressure atmosphere. So pressure goes from high to low, always. Which causes lift. Now there's another theory. Mr. Isaac Newton did not actually develop this in response to aerodynamics, but more many, many hundreds of years beforehand as a result of just plain physics. So Newton's third law says every action has an equal and opposite reaction. So the way we can visualize this, which I think is easier for everybody in general, is that the air will hit the bottom of the swing. Some of the force that it puts onto the swing will push the wing up, and the rest will continue along the bottom of the wing. So basically what's happening, the air is just pushing up, causing lift. The more air allowed to push on this bottom of the wing will make the lift increase. So, two different theories. We still don't really know for sure which one's right, if any of them are right. But for the most part, both of these will demonstrate pretty successfully how this works out. Okay. You don't have an AI lands option? I don't know. Real quick, let's see if this works, Noah. Click on location, and then click on get me lost. See if that works. I'm not entirely sure if it will. It's just a theory. Just thinking that it might change everything, but, you know, probably won't because technology is awful. You said you already kept trying that. It throws you in the air above the ocean. For now, that'll be okay, because we're not going to be landing today. If we do land, though, we'll have to figure out something else. Or it'll be landing next class. Sorry, I'm trying to figure out a way as well. None of these really make any sense. Is the email attached to your webinar account the same that I can reach you at? Mars? Yeah, that's a planet. But what I'm going to try to do, Noah, is see if there's any support on the internet for that problem, and I'm going to email that address that you have, the R Janos 42. I'm going to email that with any solutions I may find, because it's been happening to some folks. I'm not sure why. So, that being said, you can probably just deal with being over the ocean for now. We're going to just be talking about drag now. Drag being the force of flight that keeps the airplane, sort of pushes the airplane back a little bit. It resists the movement of the airplane through the air. So it's directed along the same longitudinal axis, but opposed to the direction of flight. So it's pushing back on the plane, whereas thrust would be pushing forward. Drag is really put into play here when we are landing airplanes. So along the airplane, there are a bunch of what we call control surfaces, but the most important in terms of landing is called our flaps. Those are the control surfaces that are closer to the tips of the wings. And what's interesting is that not only do they increase drag, but they also increase lift. Kind of weird to think about. You're on land now? Excellent. You had to go to Mars and leave? Okay. Well, then I won't worry about emailing you. I hope that solution keeps working for you. But the flaps increase both drag and lift, which is kind of weird. Because if we're landing, we don't want to increase lift, do we? Not really, no. So let's take a look at a cross-section of our wings here. When we're landing, we tend to keep our flaps down to maximize our drag, but this also increases our lift some. So when our flaps are up, just like I explained earlier, we have Newton over here telling us that air is going to bounce off the bottom and back. No big deal here. But when our flaps are down and our wing is more curved, the extra curvature sort of catches the air. Alright, so that not only makes it so our drag increases, so more air is being caught, so it's resisting the flow of air, reducing the movement of the aircraft. It's also catching extra air, so it does increase the lift. So when we do land, we try to decrease our lift artificially by reducing our speed. So it's kind of weird to think about. We compensate for that extra lift by decreasing our speed to reduce it. But that's why we keep flaps down when we land. Now we've got a couple different kinds of drag. The first is called parasitic drag. So parasitic drag happens just because there is a body in the air. A body being your plane, a body being maybe a baseball. If you could fly, most of your drag would be considered parasitic. It just happens when there's something in the air. Air resistance. That's parasitic drag. Okay? Now the other type of drag is called induced drag, which is drag that is caused by an increase in lift, or caused by lift in general. So if you increase the lift on your wings of your aircraft, you're also increasing the drag no matter what. It's one of the big problems in aerodynamics. We can never have anything that has absolutely zero drag in the real world. So while airplanes are designed to minimize this drag, there is still some drag. We can never get away from it, unless we're in like a vacuum and, perfect sphere, perfect center of gravity. Never happening. We just have to deal with it, work around it. So parasitic, it's just caused by being an object. Induced, it's caused by lift. And with that, we're actually able to try using a different aircraft for the first time. We're going to be using something called the King Air, which is a twin-engine aircraft, whereas the one we have been using is just a single-engine aircraft. So what we'll be doing is going into the quick flight setup, changing our aircraft by going into the general aviation folder, and choosing the King Air B200. So just switching up our aircraft real quick. We're doing this because there are some extra manual controls that we will be using to demonstrate drag. And we will be doing yet another final approach at 3 nautical miles. So King Air B200, Airport Lowy, 3 nautical miles off runway 08. When we exit this menu, we want to immediately hit P on our laptop and pause. But we're not quite ready to do any sort of test yet, because we're going to have to change these options in the upper left-hand side of your screen. We're going to change them so that we can see a couple different options we didn't have before. So we're going to go to Settings, and then Data Input and Output. You're going to be clicking the second 2 check boxes on the following lines. Line 3 for speeds. Line 13 for trim, flap, slats, and S brakes. Line 92 for wing lift. Actually, wait, I lied. Sorry, hang on. There we go. And line 67 for landing gear deployment. My bad, sorry. Because what we will be doing is comparing our velocity when our landing gear is deployed and when it is not deployed. So I want you to think about it for just a minute. Given all the stuff we've just talked about drag, will there be more drag or less drag when our landing gear has been deployed? I want you to think about it. When our landing gear is out and ready to go, will we have more drag or less drag? And if you're not sure, what you can do is hit G on your keyboard and see if your speed goes faster or slower. Less speed would be more drag. So I'm going to hold up here until someone can answer me. Will there be more drag or less drag when we have our landing gear ready? I see one right answer. And as an addendum, what kind of drag would the landing gear be? Parasitic or induced? So more drag or less drag, parasitic drag or induced drag. So I've got a couple half-right answers here. I'll go ahead and tell you that there will be more drag with the landing gear deployed, but it's not induced drag. It's actually parasitic drag. So it's kind of weird to think about it. Induced drag is just caused by lift. So if a wing is producing lift, it's also going to be producing drag, called induced drag. Now a body flying through the air produces parasitic drag. And this parasitic drag, even though you can deploy and retract your landing gears, it's just caused by the landing gear being dragged through the sky. It's actually parasitic drag. But it's a little bit hard to visualize, so don't worry. Good thought. Alright. And generally when we have more drag, our velocity will decrease on our airplane, hence why we do slow down when we land. That and because we're losing lift, or we're trying to counteract the action of lift in this case. Alright. The last thing that we're going to be doing today is testing the effects of lift and drag when we have our flaps down, or when we have them up. So in the quick flight, not the quick flight setup, sorry, in the data input and output, we're going to deselect our landing gear deployment and select lines 92 and 93 for wing lift and wing drag. So you'll have these 4 lines selected, 3, 13, 92, 93. We're going to be flying once again at our 3 nautical miles above Lowie, or from Lowie rather. And we're going to do a series of alternating tests. of the tests are going to be with the flaps up and half are going to be with the flaps down. So you will need to pay attention so I can show you how to put the flaps up or down. This is going to be the last thing we do today, so don't worry. We are going to test what happens to our lift, what happens to our drag, and what happens to our V true with our flaps up and down. So it might be beneficial if you get a pen and paper real quick so you can just write down a couple numbers. If you don't, I will go over this again next class just so you just make sure that you understand this. But what I'm going to show you real quick is how to put the flaps down in your cockpit, okay? Right next to our radio console, you'll see a button that says up and down, or a switch that says up and down. That's actually for the landing gear. Right underneath it, though, there is an unlabeled switch, which if you pull, will put the flaps down. Alright, so this is no flaps, this is with flaps deployed. Alright. You're going to test, or to check your V true, which is the second from the right. You're going to check your wing 1 lift and your wing 1 drag with your flaps not deployed. You'll do it again with your flaps deployed, and then you'll do that pattern 2 more times. So, flaps up, check your velocity, lift and drag, flaps down, velocity, lift and drag, and do that 2 more times. I'm going to discuss what exactly you should be seeing next class, but for the last 2 minutes of class, I do want you to work on that. As of 7 p.m., you are free to go. But for now, I'll be here, so if you have any questions on anything, I can address them. If you've done these 3 things, you are free to go for the day. So no worries. And I'm glad you had a good time today, Lauren. Virtual high five to you as well. Thanks for coming out, Wyatt. I'll see you on Wednesday. Alright, it is 7. If you have any last minute things, let me know. Otherwise, I will be heading out in just a moment here.